5 review on chapters 12 through 14 as far as topic sections to be covered for exam, which starts on Monday, November 30th. Okay, so I'll go through this now. First chapter, chapter 12. This. So, starting with chapter 12 on sound. All right, sections to be covered is just speed of sound in air, 12.1, air and other materials. All right, so that's basic with that. Other characteristics of loudness, pitch, that we normally associate with sound. So what do they mean? Loudness has to do with amplitude. Pitch has to do with frequency. So that's basically it there. For 12.2, that's a decibel scale. Which is a logarithmic scale. We've been through this, so it's beta, and it's in units of dB. Again, just beta is 10 log I over I naught, where I naught is the threshold of hearing of 10 to the minus 12 watts per meter squared. So extremely low intensity. And then basically everything is, as we've talked about, is a logarithmic scale. So if it's 10 times louder, it's going to be a change in 10 dB. If it's 100 times louder, it'll be 10 plus 10 or 20 dB. So that's section 10, 12.2. A little bit that loudness intensity is proportional to the inverse square of the distance, meaning if you double the distance, you will reduce the intensity by a factor of 2 squared or 4. So this is how intensity goes out. We'll see this more when we talk about light radiation, but it basically goes as a surface area as far as this is concerned. So that's just basically 12.2. Nothing in 12.3, 12.4, so I'll leave that up for a minute. So moving on. Section 12.4, standing waves and resonance. All right, just the figures we've shown. I'm not going to go through those other than you can see those. Is that standing wave, we have nodes at both ends, and the mode number so lowest frequency, first harmonic, as just one antinode, Second one has 2 antinodes, 3 has 3 antinodes, and such. So that's the part there as far as that's concerned. Just a little bit on the fundamental. Again, if this is the length, then this is L is lambda over 2, and so on. So we always have a standing waves as far as those concerned. All right. All right, that is 12. Oh, also on 12.4. So that's standing waves on a string. We also have open and closed tubes, right? Which is directly related to lab 12, right? So we did lab 12. Again, open is open at both ends, but we're generating the sound from one end. Closed tube is closed at one end, we're generating the sound from the other end. And as we discussed earlier, all right, so the characteristics, what we measure is the pressure with the microphone. So this is for an open tube, this is for a closed tube. As far as how they work, again, for the open tube, the harmonics are F is 1, 2, 3, and so on. For the closed tube, F, they're just odd, 1, 3, 5, and so on. Right. So for the closed tube, we have just odd harmonics. For the open tube, we have all of them included. So that's section 12.4. Again, refer to the figures there as far as that's concerned. Okay. All right. And again, referring to lab 12. All right, for 12.5. That is quality of sound, and superposition, all right, so basically what's the difference between a tuning fork, all right, a violin, and piano, if we play middle C. So playing middle C, what's the difference of that? The fact that you have higher overtones and harmonics that combine in a certain way, as we had in the figures, right? When we plot a clarinet, piano, violin, how that works. Well, a tuning fork has just one frequency. A violin or piano has multiple ones added in such a way that you have the characteristic sound of that. So that's 12.5. 12.6 is beats. And that is where the beat frequency is F beat is F1 minus F2, and they need to be relatively close in frequency, so generally less than, I would say even 10 to 15 to be heard. So the beat frequency has to be less than about 10 to 15 to be heard. Otherwise, you can't hear the raising and lower the sound. So that's beat frequency, that's section 12.6. 12.7, Doppler effect. And I'm not going to go through all the equations again. All right, but you have the fact of if you are, in this case, something standing here, so you're the observer, source. All right, it's moving towards you. The source is moving towards you. You have a higher frequency. If it's moving away, so if you're on this side, that's that way. F, this is F naught. F is less than F naught. Here, F is greater than F naught. And we have the formulas for that. And in this case, we either have the source moving or the observer is moving. Again, if you're moving towards it, you're going to have a higher frequency. And the expressions we have for that, as I mentioned before, are on the 7th edition on page 346. So I've shown these equations talking about chapter 12 for calculating precisely what the frequency is. It's not going to be an overly huge change as far as that's concerned. So we've already discussed these. You have the equations related to that, so be careful what you are doing. And in all of these, we have speed of sound is generally 344 meters per second when we're using those things, right? And then the speed of the observer, the source, is those requirements. Okay, so that's section 12.7. And that's about it. So the only thing you might want to look at is a section on sonic booms. And this is the case of where section 12.8 occurs when you travel faster than the speed of sound. Such as a jet fire going 1,000 miles per hour, speed of sound is 750, you build up this sound wave ahead of the jet, and it produces a boom, which can be annoying, can break windows and stuff. And that's section 12.8. And if there's any questions, that'd be just on a qualitative basis. So. And the speed of 344 meters per second, or about 750 miles per hour. So that is section chapter 12. Okay, so leave that up, and then move on to the next chapter. And that is temperature and kinetic theory, chapter 12, chapter 13, temperature and kinetic theory. I'm not going to go into the details of that. Again, we have 13.2. Temperature scales, Fahrenheit scale, Celsius scale, Kelvin scale, and the relationship between all three of these as far as that's concerned. The fact that Kelvin is Celsius plus 273, and this is primarily what we're going to be using here. We do the gas laws, we use Kelvin scale, For other things, we use the Celsius scale. And for what we use in America is the Fahrenheit scale. Okay. 13.4, thermal expansion. And our formulas of delta L is alpha L naught delta T, where T can be the degrees Celsius, degrees Kelvin difference, because we're only looking at a change. This is for linear, and for volume, it's beta times V naught times delta T. So if you have a liquid, this is the expression we use, or if you have a solid and we want to look at the volume, changing volume of it, this is the expression, and that's for that. And then if there are any numbers you need, I'll give those to you in the test as far as calculating that. So that's section 13.4. Okay. Moving on here. The ideal gas law. All right. So 13.5 and 6. So 13.5, 6, ideal gas law. All right, PV equals nRT. Again, P, for most of the problems we're using, P is in atmospheres, V is in liters, N is in moles, R is the gas constant, 0.0821, and T is in degrees Kelvin. All right, so that's the one I'll be using because that's what you use most generally in chemistry. And we have to use degrees Kelvin because if the temperature, it makes no sense to have a temperature less than 0 like we would have a Celsius scale. All right, so this is the reason why we have that. So that's the ideal gas law, and then partially it's just problems related to that. That's all there is to that. I'm not going to do 13.8, which relates to the ideal gas law in terms of Avogadro's number and other kind, because that's what we use in physics. So set 13.8 is what I use in physics, but for this class, this is supposed to be a chemist and biologist. This is the expression we'll be using. All right, and finally, 13.9. I believe this is the last section. Yeah. Is kinetic energy is proportional to temperature. Now it's equal to 1/2 mv squared, which is also equal to 3/2 kT. So we measure kinetic energy by measuring the temperature. Again, this is the average, should say the average of that. So what we actually have is a distribution. And I talked about this, about why we have no helium and hydrogen, because in a distribution, some of them are very hot, they have very high speeds, so they can escape the Earth's atmosphere. And you can see from here again, the temperature has nothing to do with the molecule itself. It's just that the lighter the mass, the faster it's going to be going to the same temperature, okay? Or the same kinetic energy. And that's just what we've had before. Light masses have to go very fast to have a high kinetic energy. So that is all of chapter 13 is concerned. So there isn't a whole lot to it, right? And most of this chapter, this section is going to be on a qualitative basis. All right. Moving on to the final chapter then. For this semester. All right, 14 is heat. All right, again, 14.1, relationship in between, we talked about heat and energy. All right, we've had potential energy, kinetic energy, and so again, the relationship between potential and equivalent heat. So again, 4.186 joules is 1 calorie. So that's part of that definition, connecting heat energy in, say, water, and how that can convert to mechanical energy of MGH, potential energy. So that we talked about that before already. Internal energy, so 14.2, internal energy. U is given by 3/2 nRT, where again R is the gas constant we've had before. So this is the internal energy, and this will be in either joules or calories. And again, both of these are units of energy. All right, so that's 14.2. 14.3 is just specific heat. And this goes back to the extra credit lab I did. That's still open on specific heat, latent heat. And again, Q, which we use for heat, is MC delta T, where M is the mass, C is the specific heat, and delta T is the change in temperature. Again, for specific heat, we're going to be using mostly calories because it works out. For water, it's 1 calorie per gram degrees Celsius. That's what we're going to be using for this semester. We get into chapter 15 next semester. We'll be using units, joules, and kilograms. But for this semester, we're going to do it because it works out very simply. So this is for water, H2O, and the table 14.1, which again, if I ask a question, I'll just, it has different specific heats. That's 14.2, 3 I should say. We did problems related to that. That's also 14.4. All right, so mixing, so nothing too complicated there. We've done some examples there. So, leave that up for a minute. All right, we'll move on to next part. All right, 14.5 is latent heat. Okay, and for latent heat, that is given by Q is MLF or MLV, where again, this is fusion, so ice to water, again, LF. We're mostly going to be doing water for this, so 80 calories per gram. Latent heat of vaporization is 540 calories per gram. Again, we've talked about that and some examples related to that. The problems we have that I talked about for chapter 14. So I'm not going to go into any details there, but again, we're going to be using calories and grams for this semester. Okay, and then examples related to that. Oh, and then the last sections, 14, 6, 7, and 8. 6 has to do with these are all heat transfer. So this 6 is on conduction. 7 is on convection. And 8 is on radiation. Gone through that. All right, again, most of these will be a qualitative basis, like what are the characteristics of conduction, convection, and radiation? What type of conditions make those work best? And as far as, just more or less intuitive, temperature difference, obviously for these two is going to be a bit better. What do we mean by radiation? This is always electromagnetic radiation, E&M radiation, which we'll get into more in next semester. We talk about light and such and black body radiators, or in later chapters in the book. So I think, yeah. So that is all for the exam. It's going to be all multiple choice again for this 5th exam. Again, I'm dropping the lowest exam score after this. So, and then the final exam, which I'll do a short review, will be based on all the chapters. So that's exam 5. Otherwise, have a good holiday. Be careful and have